Hey, good morning. Hope everyone's doing well.
You're right, Nick. How you doing?
Doing pretty well. So my printed circuit boards are apparently lost by DHL, but I redesigned them and reordered them, and they were remanufactured, and the replacement ones are supposed to show up today, which is cool. So I'll be playing with those this afternoon, which will be awesomeness. All right, let's see. Question. Have you gone over how to designate a new root in class? What do you mean by a new root? Are you talking about when you're adding data to a tree? How to create a new node? So that might be the question.
Sorry.
Oh, there you go.
Oh,
Yeah, so what do you mean by a new root? Okay. Give you a second. Here, I'll show you my super exciting
okay.
circuit board. There we go. All
So,
right, go ahead.
so, basically, I was thinking about, yeah, adding a new root, like adding a new node for one, but
Mm-hmm.
also, like when you initialize. But also, I was thinking, throughout the PA4 document, it says, um, how to designate a new question mark root, which means if you need it. So like if you have the new lowest number, how do you designate a new root and then kind of restructure, or not even restructure, just like have the root point to a new left or a new right, depending.
So, let's see. So remember, with tree insertion, we want to do this recursively, right? So, so we've got an add function that's going to take a root node, which is a pointer to a node, some kind of data, which for PA4 will be license plate, first name and last name, right? And this is going to return a node pointer, and if the data is less than the root node's data, so for we're keying on license plates, so you're going to use string compare. So if string compare data comma root arrow, or plate comma root arrow plate, right, is less than 0, then we want to insert on the left. And so that's just going to be a straight recursion, right? We're going to say root left equals add root left data. And then we're just going to return the root. And we're going to do a symmetric thing if the data we're adding is bigger than the root, right? Our edge case, which is where your question comes in, is if the root is null, right? I think this is where your question comes in. So if the root is null, we need to create a new root, right? And what do we do in that case? Call malloc. Allocate enough space for a root node. So that's going to be size of struct, whatever your T node is. And then copy the plate, the last name, and the first name to this new root, and then return that new root as the value of the add function. So this is the only spot where a node actually gets created, right? Which is when you try to add to a tree that's empty. And to create the node, do a malloc to make space for the root itself. If you're doing this with trees of integers to practice, right, then copying the data is just, you know, root arrow data equals number, and get that working first. But then when you're doing PA4 and you need to deal with license plate first name, last name, you have to use string copy to copy those. Don't use equals, because equals is just, you know, setting a pointer. You want to use string copy, but before you can do that, you need to allocate space. So you're going to end up doing something like root arrow plate equals malloc. And you need to look at the length of, you know, maybe in plate, whatever your incoming plate is that was passed to your add function. So find the length of that, add 1 for a null terminator, allocate that much space, have root's plate field point to that, and then do your string copy, root arrow plate, and in plate. Where in plate was, you know, one of your arguments to your add function. And you can assume that the plate is not already in the tree. So you're being given a database file of license plates. You can assume the license plates are all unique in there. This I would not do as an else. This really has to be the first statement, because if root is null and I try to look at root arrow data, I'm going to segfault right there. So really the first thing you want to do in your add statement is see if the root is null. If the root is null, then go ahead and do a malloc, make space for your fields, copy them, and so on. Otherwise, if the root is less than you know, the data, otherwise if the root is bigger than the data, and one of those three will definitely take place. And the add part is other than delete, which is a whole different level. The add part is the really trickiest part, because it's the function where we change the structure of the tree. Traversal, search, we don't have to change. We just look at the tree and examine what's in there. But add, we're actually modifying the structure. And the nature of that modification is peculiar because it uses this, right? The fact that the add function returns a root. And that kicks in right here when we create a new node to be the root of a previously empty tree, and we return that root. And remember, in main, when you call your add function, you have to call it like this. Right, whatever you're calling your tree, I'm calling it root here, for example. You pass that to your add function, but you also set that to be equal to what the add function returns. If you don't do that, if you just call add, your tree will always be empty, even though your add function is doing a lot of work. All right, good. Other questions? All right, let's look at ODP 215. So 215, which is due tomorrow morning at 10. This is this is related to a piece of your delete function. Okay. Remember, when we delete a node from a binary tree, most of our delete code is recursive, right? Mostly we're saying if the thing we're deleting is smaller than the root, then delete this node from the left subtree and patch up what our root node is pointing to on the left. If the thing we're deleting is bigger than our root node, delete it from the right subtree. But if the thing we're deleting is the root of the tree, then we do all of that work that we talked about last week for actually removing a node. And the way we remove the root node is we replace it with the largest node from the left. And we have that largest node's left child adopted by its parent and all that sort of stuff. This is a subset of that work. ODP 215 is strictly saying write a function that you can hand the root of a tree and it will tell you the value, the data value of the largest node in the left subtree. All right, so take in a root, right? You're writing this function called largest, takes in a root of a tree, and what you should do is you should move to the left subtree of that root, which you're guaranteed will exist. Okay, it's not going to be null. So move to the left subtree and then find the largest thing in that subtree. Okay, the algorithm we went over in class was start at the root of the left subtree and just keep moving as far right as you can. So here's a tree. And if you want to find the largest thing in this tree, the largest thing in the left subtree, right, start from the root, move down to its left child, which will not be null, and now just think of these right children as forming a linked list. So see what this thing's right child is. If it's not null, move down there. See what that thing's right child is. If it's not null, move down there. See what that thing's right child is. If it's not null, move down there. See what this thing's right child is. Oh, it's null. Return this thing's data field. Okay. So just follow the right pointers and return the largest thing that the last thing that you find in that chain of right pointers. Okay. That is guaranteed to be the largest thing in this whole subtree. All right. Only trick is you're given a root to the entire tree. First thing you have to do is move left one spot and then start moving to the right. So that's a piece of what you'll want to do in your delete algorithm. The delete algorithm is a little different because it has special cases. You have to deal with the case where there's nothing to the left. You have to deal with well, that's the only case you have to deal with. But you have to, in the case of deleting, you have to actually do something more than just return the value of that largest node. You have to actually change that node into the root. And in this case, 25 would become the root, but 25 has stuff on the left that would be adopted by 25's parent. So this link would change to that. But you don't need that for this assignment. All right, any questions on 215? All right, so let's talk about sorting. This is our topic for the next few days. How do we sort data using a computer? And sorting is a classic problem. It goes back in some sense to the origins of mechanical computing back in the 1800s with the census and Hollerith, who developed a mechanical machine for counting census data. And these things were put on Hollerith cards, we call them now, sometimes called IBM cards, but they were punch cards. And data was recorded on them by putting holes in them, and there was a machine that would tabulate these and that could be used to generate census information. Well, that involves sorting. If you have I don't know if they had zip codes in the 1800s or not, but if you had data sorted by that included zip codes and you wanted to find population in different parts of the country, you would probably sort it on something like zip code. And then, you know, here's the one zip code and here's another zip code. Well, this has more population than that one, right? So sorting is a very old problem. And there's a lot of different ways to sort data. And the first one that we usually encounter, which we do in CSE222 is what? What's the sort of fundamental sort that you might think of? Bubble sort, right? That's kind of the go-to. I don't think, other than for the sake of lecture, I don't think I've ever coded anything other than a bubble sort. That's my confession for the day, right? Bubble sorts are really easy to code up. They're terrible performance-wise, but you know, if I'm sorting 1,000 things, I don't care about performance. You know, I could have order n cubed performance in 1,000 things, not going to be a problem. And if I need to sort a lot of data in a really quick way, I'm not going to write my own code. I'm going to use a sort algorithm from a library, or you know, something from the operating system, or something like that. But the underlying is, yeah, there are a lot of sorting algorithms, and there's some really good videos available that go over different types of algorithms. There's some with Romanian dancers that are particularly favorites. Lots of different algorithms for sorting. Why do we have so many different ways to sort? Well, you know, your goal is the same. You want to take this data and put it in, say, increasing order, right? Or alphabetical order, or something. But depending on the nature of the data and the size of the data, different algorithms will have different performance characteristics. So for example, if you have a small amount of data, a bubble sort is really easy to implement, and it works pretty well. If you have 1,000,000 pieces of data, you don't want to do a bubble sort. Bubble sort's going to take you a really long time. You might want to do something like a merge sort or a quick sort. But merge sort, quick sort, fair amount of overhead. And if you're just trying to sort, you know, 1,000 numbers, it's quicker just to code up a bubble sort. An insertion sort takes roughly the same amount of time as a bubble sort. They're what we call order n squared. But an insertion sort, if your data is sorted to begin with, might work really well. It might go down to like an order n. A quick sort, which is better than all of these sorts, works really well unless your data is close to sorted to begin with. And if your data is close to sorted, quick sort becomes something on par with a bubble sort. So someone said memory versus speed, the eternal battle. Absolutely. To me, it's not so much memory as it is space. Because, you know, the issue with memory is that it takes physical space, but there's other things we can do that might not use memory per se, but still take physical spaces. And so I would rephrase that as space versus time. And that to me is the quintessential battle, right? The struggle for finding a sweet spot for algorithms. Where do you want to fall on the space-time curve? And so yeah, so some jobs need to be done without speed being a factor. In the 60s, right, we didn't have hard drives, right? Where was data stored? Data was stored on magnetic tapes. How many people here have had a cassette tape recorder in their life, or a reel-to-reel? You can still buy cassette recorders, which is awesome. Okay, there's a really goofy drawing of a magnetic tape, and you know, there's a read-write head, and you've got a bunch of data stored on here. You got a bunch of names, and you want to alphabetize them, right? the thing with magnetic tape is I can't just say, hey, give me this piece of data right here. Okay, now give me this piece of data. Okay, now let me look at this piece of data, right? To get to that piece of data, you have to unwind this whole spool until this point of the tape hits your read-write head. You people are making me feel old. Right? So a hard drive, right? We have two-dimensional access. The disk is spinning, right? But we also have a read-write head that can move forward and backwards. Right? So worst case, we have to move from the outside to somewhere in the inside, and we have to wait for this sector to rotate to where we can read it. On a magnetic tape, this was one-dimensional. If I was sitting here all the way at this end of the tape and I wanted to read a piece of data from the other end, which might be, you know, 1,000 feet away in tape distance, I'd have to spin that whole tape and get that piece of mylar to go under my read-write head. So when you're storing your data like this, your sorting algorithms have to be optimized in such a way that you don't need to compare pieces of data that are physically far apart from each other. And a bubble sort would work really nicely for this. Because what do you do in a bubble sort? You start at the beginning and you compare a piece of data to the number right after it. And if they're out of order, you swap them. Well, that's easy to do on a tape. Some of these other algorithms that we're going to talk about, which theoretically have a better performance, require you to be able to bounce around from one end of the data to the other. And that works terribly on something like magnetic tape. So there's lots of different characteristics that can come into play. So let's look at some algorithms. Let's start with a bubble sort. And the idea of a bubble sort, so let me use my deck of vintage cards here. Let's say we want to sort from smallest on top to largest on bottom. Okay, and I'm going to take out my Jack, Queen, King, just to simplify. So I want to sort from smallest on top, largest on bottom. So what's a bubble sort do? We look at the first card, we compare it to the second. Our goal is to have smaller cards on top. Well, a 1 is smaller than a 2, so these are in the wrong order relative to each other, so we're going to swap them. Okay, a 2 is smaller than a 10, that's fine. Let's look at the 10. 10 is bigger than 4, so it should be on the bottom, so we're going to swap the 10 and the 4. 10 is bigger than 3, so we're going to swap those. 10 is bigger than 5, we're going to swap. 10 is actually bigger than 9, so we'll swap. It's bigger than 8. It's bigger than 6. It's bigger than 7. And now there's nothing left to compare it to. What we've just done is we've moved the largest piece of data to the end of the array. So this is what we call one pass through the data. And after one pass, the largest number in the array is at the bottom, which is where we want it, because we're sorting smallest to largest. If we make a second pass, what's going to happen, the largest number in this pile, which is the second largest number in the original data set, will move to the bottom of this pile, which is where it should go. So compare 1 to 2. 1 is smaller, that's fine. 2 is smaller than 4, that's fine. 4 is bigger than 3, so we have to swap those. 4 is smaller than 5. 5 is smaller than 9. 9 is bigger than 8, so swap. 9 is bigger than 6, so swap. 9 is bigger than 7, so swap. And now 9 is in the correct position. And you can see what's happening, right? If my large number is sitting in the beginning of my pile, I'm going to swap it with more and more numbers, working my way through my array until it gets down to the right spot. So if you think of rocks in water, right, the heavy rocks are sinking down and eventually the lighter rocks are bubbling up, right? So that's where I think of the bubble part of a bubble sort. So we have an inner pass. So we run some index from 1 to n. And the idea is compare and possibly swap data I with data I plus 1. And I'm going to be really sloppy with edges here. I'm not going to worry about should this be n or n minus 1, should this be a 0 or a 1. I'm not going to worry about those kinds of details. I'm looking for kind of overarching coarse measurements here. So this inner pass, which takes, one piece of data and moves it down into the correct spot, right, is a for loop that basically goes through all the pieces of data, compares each number with a number after it in the array, swaps them if they're in the wrong order. And after this inner pass, we've moved one more piece of data into the correct spot. Well, if we have n pieces of data, then we need to potentially do n passes. So we do this inner step n times, and after that we're guaranteed our whole set of data is in the correct order. So this inner loop will happen n times. And if we do that inner loop n times, right, this outer loop executes n times. That's a total of n times n, which is n squared times that we do this comparison and possible swapping of two numbers. And so this is called an order n squared algorithm. So order of complexity. Not great, but for small n, not bad. But let's remind ourselves what the significance of n squared is. If we have three pieces of data, that inner loop, right, to move one number into the right spot runs 3 times. And we do a total of 3 passes. 3 times 3, this is going to be 9 operations that we perform. If we have 6 pieces of data, our inner loop takes 6 iterations of a loop, and we do that inner loop 6 times. So this is 36 times we execute our loop. And here's the part that hurts. We double the amount of data, we quadruple the amount of time. All right, this is the essence in which this is quadratic. If we did this for 10 times as much data, it would take 100 times as long. So the question in chat is, how long is n squared units? No idea, right? This will be very different if this is running on a mechanical Hollerith machine from the 1800s or, a gaming laptop from 2021. The total time will be significantly different. But the rate at which the problem gets longer compared to how the size of the data grows, that's what we're capturing here with this order of complexity measure. Supercomputer in Canada. Okay. Right? And whether this took, 3 hours 9 hours for 3 pieces of data, 36 hours for 6 pieces of data, or it takes 9 picoseconds versus 36 picoseconds, right? The part that we can measure without worrying about units is a 4x increase in time for a 2x increase in data. So that's the n squared essence. Now, when we do a bubble sort, we can get fancy, right? We don't need to go through all n pieces of data each time we do this inner pass. So let's say we have 10 pieces of data to sort, and we're going to use a bubble sort. Well, the first time through, we actually only need to do 9 comparisons. Right? We're comparing the first number to the second, second to third, third to fourth, and so on. The last comparison is the 9th to the 10th. So we're only doing 9 comparisons for our first pass, and we know after our first pass, our largest number is going to be at the bottom of the array. So the next pass through, we don't actually need to compare anything to that largest number. We're only going to have to do 8 comparisons. And the next time through we'll only do 7, and the next time through we'll only do 6. And the final pass we'll only have to do 1 comparison, which is just to compare the first 2 entries in our array. And so if you do this, this looks more like n squared over 2. But as far as growth rates, n squared over 2 is the same as n squared. Because if this is n squared over 2, this is 4.5, this is 18, it's still a 4x increase. So when we calculate these orders of complexity, we tend to throw away constants. So a constant multiplier is going to not affect the quadratic term. And if we found something like n squared plus n, that's going to end up being about the same as n squared, because as n gets really big, this becomes so much more significant than that. Yeah, if n is 5, this is 30 versus 25. That's a pretty big difference. But if n is a billion, right, this is 10 to the 18th, this is 10 to the 18th plus, something 9 decimal places down the road, right? And it's being dominated by the n squared term. So we use pretty loose approximations for these. Now, when you do an algorithms class, you'll dig into these in a lot of detail. But for 222, right, we're just going to go with rough approximations. And so bubble is going to be on the order of n squared. All right, so there's 2 other sorts that are similar to bubble sort. And they're pretty straightforward to code up, and they're equally as poor performing. So insertion sort and selection sort. Yeah, I knew I misspelled selection. And they're almost the same, which means they're really easy to get confused, at least for me. So for both of these sorts, we're going to start with an input array, and we're going to move data from the input array to an output array. And when we're done, our output array should be sorted. So where does the sorting happen? Well, it can happen in one of 2 places. It can happen when I choose which card to move next, or it can happen when I choose where to place that card in the output. Okay, 2 fundamentally different operations. So let's talk about selection. Selection sort, the sorting happens when I select a card to move. Okay, so the sorting happens when I make my selection. So how do I select? Let's say I want to go from smallest to largest. Okay, I'm going to go through my entire input array. I'm going to select the largest thing in there. All right. Well, top card is 2. So to begin my algorithm, I'm going to say 2 is my largest number in my array. Okay. Hey, 8 is bigger. 8's my largest number. 8 is still my largest. 8 is still my largest. Yep, looks like 8's my largest piece of data. Hey, there's a 9. 9 is my largest piece of data. Okay, 7. Oh, 10. 10 is my largest piece of data. I'm done. I'm out of input. What's my largest piece of data? 10. Okay, I take that. I put that at the end of my output array. That's one pass. And we do this n times. 10 in this case. Exactly the same thing the next pass. Find the largest piece of data in your input. Okay, I think it's a 2. Oh no, I mean it's an 8. It's an 8, it's an 8, an 8, 8, 8, 8. Oh, there's a 9. 9's my biggest. 9's my biggest. Okay, 9 was my biggest. All right, we'll take that. We'll put that on our output. All right, so what are we doing? So we do a total of n passes. Pick largest number in the input and add to the output. Now you need to do some work to do this in a computer instead of with playing cards, right? So I want to find my largest number in here. Well, there's an 8, and that's going to end up being my largest. So, you know, I need to have a variable that represents my largest number. I'll initialize it to 2, and each piece of data, if it's bigger than what my largest is so far, I'll set my largest equal to that, right? I also need to know where I found that largest piece of data. So I start off with a 2, that's my first card. There's an 8, that's my second card. I need to know the value is 8 and its position is, you know, the second number in my input array. So that when I go through all of this and I decide 8 was my largest, I know where to take it from. I take it from the second place. And I put it in my output. And you need some way to remove this number from the input array. Well, arrays don't really work like that, right? You can't really just delete something in the middle of the array, right? We're not physically moving something from one array to another. We're copying it, right? But how do you delete from an array? Well, you take the thing you want to delete, you swap it with the last element in the array, and then you say, okay, my array only has this much stuff. You shorten your array by one element. Or something like that, right? Or maybe you're using a linked list. Because we're just going through this sequentially, and we know we can remove something from a linked list in a fixed amount of time. So if we're going through the list every time, aren't we just allocating space for a new array and keeping the same time order? It's going to end up being n squared. Yeah, it is the same as a bubble sort, actually. Because each pass requires us to go through, you know, every piece of data in the array to find our largest. And assuming that, you know, we can just put it in the next spot in the pile, then we have to do a total of n passes to pull out all n pieces of data. So this ends up being an order n squared. But there's more mechanics to take care of. This business of adding something to your output array and somehow removing it from your input array. And there's all kinds of funky things you can do. You can actually do this with a single array and be building up your output array from the bottom, because as you remove things from your input, you don't need those bottom spaces in the output. And again, this depends on, you know, how much data you have. Are you able to move around from one spot in your data array to the other end, and so on and so forth. All right, so that's selection. The sorting happens when you select which piece of data to move. The other version of this is insertion. And with insertion sort, the sorting happens when you choose something from your input array. So we start off and we try to find, sorry, that's selection. Insertion happens when you move your card into the output array. So insertion sort, you always just take the first card from your input, right? So take element 0 or maybe element n, right? And put it in your output array so that your output remains sorted. So first number, our output array is empty, so 2 goes right there. Okay, take the next number. I'm just going to take the first element in the array, that's a 7. I can't put it on top of the 2 because it's bigger than 2, so it has to go below, and there's nothing below, so I'm going to put it right there. Take the first card, figure out where to insert it in your output array. Well, it's got to go below the 2, and the next card is a 7, it should go above that, so I'm going to put it right there. And so each time that I make a pass, I'm taking one card from my input array, I'm inserting it into my output in the right spot. So my output array is always sorted, but the sorting is happening when I insert into this output pile. So there's a 3, it should come after a 2, comes before a 5, so it goes right there. There's a 1, no work to do, I know it goes right before the 2. There's an 8, so it comes after the 1, after the 2, after the 3, after the 5, after the 7. That's the end of the pile, so it goes right there. And so this is order n squared also. Picking a card from the input pile, that's order 1. I'm just going to take the top card. But to figure out where it goes in my output pile, well, if it's smaller than the first card, it takes 1 operation. If it's larger than the last card, I'm going to have to look at every card in my output pile to decide, oh, this goes at the bottom of that output array. So best case 1 operation, worst case n, average n over 2. And since I have n cards to process, that's going to be average n times n over 2, so n squared over 2, which is the same as order n. So similar order of complexity. But here's an interesting question. What if our data is almost sorted to begin with? What if our data was mostly sorted and, maybe 1 or 2 pieces of new data came in and got, added to the beginning or the end? And so most of our data is sorted, but maybe there's an 8 sitting up here, right? Okay, so what does a bubble sort do? It compares, 2 pieces of data. 8 is bigger than 1, so that's fine. 8 is bigger than 2, so those swap. Bigger than 3, bigger than 4, bigger than 5, bigger than 6, bigger than 7, smaller than 9, 9 is smaller than 10. Okay, 1 pass, right? Second pass, ace is smaller than 2, 2 smaller than 3, 3 smaller than 4. We do our comparison. And when we get to the end, if we observe that we did not swap anything, we can say we're done. So we can modify our bubble sort and put an extra step in here, which says let's set a flag every time that we swap. And our outer pass can be while that flag has been set by the previous pass. And if we make that small change, a bubble sort will work really well on data that's almost sorted. Because we'll move, the few things that are out of place into their right spot, and and then we're done. All right, what about a selection sort? Selection sort, remember, we're picking, say, the largest thing in this pile and moving it to the output. Well, if our data happens to be sorted, right, either in increasing order or in decreasing order, it doesn't make any difference. We don't know what the largest thing in here is until we've compared, you know, with every single card in the input. So I might have my largest thing sitting on top. I don't know that's my largest until I compare it to everything in here. And certainly if my largest is the last card, I'm not going to find that until I've gone through everything in here. So even if our data is perfectly sorted to begin with, each of these inner passes of our selection sort will still take n operations, and we do n passes. That's going to be an order n squared. Now we can add extra stuff, you know, to observe, for example, that this was in order as we went through. But since we're building an output pile, right, the sortedness of the input pile doesn't really come into play. On the other hand, an insertion sort can do really well. So suppose we're starting with our data sorted exactly opposite how we want. So remember, insertion sort, we simply pick off the first piece of data from the input and we insert it into the output so that it's in the right spot. So we would pick off this 10, there's nothing in the output, so it goes right there. That's one operation. Second pass, we pick off the first card and we try to insert it into the output pile. Well, we look at the first card and that's bigger than a 9, so we know the 9 goes there. That was one operation for that pass. Third pass, we'll take the top card off of the input, we'll compare it to the first piece of data in the output, and it goes right before it. So for an insertion sort, each of these inner passes might only take a single step. And so if we have n of these passes to do, that might turn out to be order n. Now you can lose that time if when you're adding to your output pile you have to move things around in your array. But there's ways you can avoid that, or you know, you could be using a linked list instead of an array or a deck of cards in your hand. And so insertion sort can actually benefit if your data is extremely unsorted to begin with, if it's actually sorted in the opposite order. Or depending on, you know, which end of the array you're starting from, if it's sorted in order, you can also get a performance boost. So why do we care about sorting? Well, it's a classic problem in computer science, right? Like I said, it goes back to, you know, some of the earliest mechanical systems. It's a good way to look at algorithms. It's a good way to compare, you know, performance characteristics of different algorithms. Look at how time changes with problem size and so on and so forth. It's also a really good way to look at more examples of recursive algorithms. And so what I want to look at tomorrow is a different set of sorting algorithms. I want to look at something called a quick sort and something called a merge sort. And these are better than order n. These tend to be order n log n, which is a manageable complexity. And they're recursive in nature. Part of the merge sort algorithm includes calling a merge sort, and part of quick sort includes calling quick sort. So this will be another opportunity to look at recursive code and recursive algorithms and think about this general concept of taking a problem and breaking it into subproblems and tackling those subproblems with the same algorithm that tackles the original problem. So that's the heart of recursion. All right, so we'll start with those tomorrow. I will let you out of here 30 seconds early. Have a good one. I'll see you in 2:15, or I will see you tomorrow.